Hello everyone. My name is Anil Khanel and I will be your host for today's session. This talk is organized by St. Xavier's College as a part of the course on General Theory of Relativity. Students from BSc and MSc programs at various universities in Nepal are participating in this course. I would like to express my gratitude to St. Xavier's College and our head of physics department, Basudev sir, for making this course possible at St. Xavier's College in Nepal. It's my pleasure to introduce today's speaker, Professor T.R. Sheshadri. In 1983, Professor T.R. Sheshadri enrolled in MSc program at IIT Delhi. After completing his MSc in physics, he joined a PhD program at TIFR in 1983, supervised by Professor Thanu Padmanabhan. Immediately after completing his PhD, he pursued his postdoc from University of Delhi and then from University of Sussex, Brington. And then in 1992, he joined HRI, Harish Chandra Research Institute in Allahabad, and later returned to University of Delhi in 2001. Since then, he has been a professor at Delhi University. His research focuses on inflation, CMB, cosmic microwave background, and various aspects of astrophysics. And we are fortunate to have you here with us. Now, I'd like to invite Professor T.R. Sheshadri to deliver his talk. Okay, Shish, I think we can start.
Hello, everyone. Am I audible?
Yes, Shish, yeah.
Yeah. Thanks a lot for this generous introduction. See, when the introduction becomes longer and longer, you realize that you become older and older. Okay. So, yeah. Thanks for coming so that I can torture you people. So, what I will talk on is today is an interesting aspect of the universe which goes under the name of cosmic microwave background radiation. So, what I will do is I will give the general setting for cosmology and then discuss the behavior of radiation and matter in such a homogeneous isotropic universe. And from their interaction, I will gradually take you to the origin of, a background radiation, which we all receive from all directions. And this is a remnant of the early universe. Then I will discuss how this radiation can be used to learn about various physical processes in the universe. And lastly, I will end with what is it that today, how do you understand the universe today and its constituents using this microwave background. So to begin with, so I will share my screen. Yeah. You can see my screen?
Yes, yes, yeah.
Okay. So there are three interesting aspects of our universe. One is that the universe is homogeneous and isotropic over cosmic scales. Now, what do you mean by homogeneous over cosmic scales? And in order to explain this, let me go to an analogy of a well-maintained lawn. Now, if you see a nice, well-maintained lawn, you say it is well-maintained because the greenery is uniform everywhere. But if you ask an insect, the insect will differ. The insect will not see the uniform, the lawn to be uniform. What is the difference in perception? The insect, when it is sitting in the lawn, it sees a rough patch, a brown patch, a dry patch, and next to it sees a blade of grass. So it says that the grass, that the lawn is not uniform everywhere. There are dry patches and there are patches where there is greenery. However, when you look at the lawn, you feel it is uniform. The difference in perception lies over the length scale we are comparing. In the case of an insect, very roughly, we can say that it probably considers a 1 inch by 1 inch patch, which is dry, a next 1 inch by 1 inch patch, which is green, and it says it is inhomogeneous. But when we look at the lawn, the way we perceive it is we don't average the greenery in such a small region. We inadvertently, mentally, we divide the lawn, say, into squares of 1 meter by 1 meter, average the greenery in each square, and compare this average greenery from one square to another. And this average greenery from this large square, one to another, is almost identical. And so we say that the lawn is uniformly green. The moral of the story is that saying that something is homogeneous is not a completely well defined statement. What you need to qualify is when you say something is homogeneous or uniform, you have to specify over what scale you are talking about.
Shesh, I think you are mute. You can unmute. Okay, okay. Hey, Shesh. Yeah, I think you are on mute, I guess.
Okay.
No, no,
So
fine, fine.
when I when so when we look at a lawn, we at the length scale we are comparing is about 1 meter size. Now, similarly, in the case of universe, when we say, just a minute, when we say that the universe is homogeneous, there must be a length scale over which we are comparing the constituents of the universe. So in the case of universe, it turns out that just like I had the 1 meter by 1 meter square of lawn, in the case of the universe, the length scale over which the universe is homogeneous over scales of the length scales over which the universe is homogeneous is 100 megaparsecs. Anil, have you told them about what a megaparsec is?
No, Shesh, no.
Okay. So this megaparsec is a unit of distance. So let us see what kind of size is this. We know that the speed of light is 3 into 10 to the power 10 meters, sorry, 10 to the power 8 meters per second. And the distance traveled by light in 1 year is equal to the, so it is 86400 seconds, 86400 seconds in a day, multiplied by 365 days, multiplied by 3 into 10 to the power 8 meters. This is equal to 1 light year. Roughly, 1 parsec is equal to 3 light years. And now we are talking about 100 megaparsec, which is 100 into 10 to the power 6, which means 10 to the power 8 parsecs. Okay. So you see the enormity of scale. Now, if you consider the universe and divide it into cubes of 100 megaparsec size, average the density of the universe in each cube and compare this average density from one cube to another, then you will find that this average density is same everywhere. Just like the greenery in the lawn was same from 1 square meter to another square meter. So you say that the universe is homogeneous over scales of 100 megaparsecs. I mean, if there is any problem, please feel free to interrupt. Huh? Yeah, I would like to have this more as a discussion rather than a talk. Now, there is another interesting aspect of the universe, which is that within this uniform homogeneous structure, the uniform distribution of matter, there are structures over various scales. First of all, we have things like planets, stars, star clusters, etc. And then we have galaxies, clusters of galaxies, clusters, and superclusters of galaxies, and so on. Now, I have put them in two different columns and with two different colors, not because I have space and I have colors there, but there is a specific reason why one has done it this way. These structures, which are in this column here, the physics of their formation not just includes gravity, but various other physical phenomena such as fluid dynamics, plasma physics, and various other things. Whereas these structures involve almost entirely gravity with other forces playing a very subdominant or negligible role. And it is these clusters which are collectively called large-scale structures. And it is these structures which we are interested in when we are talking about cosmology. In other words, when talking about cosmology, galaxy is probably the smallest structure we will talk about. So a galaxy will be represented by a point in a numerical simulation. And that is because you are not bothered about the substructures of galaxy. Just like when you are doing usual, like ideal gas, you consider molecules as point objects. Why is it so? Because when you are considering an ideal gas, you are not bothered about the structures within the molecule, atoms or electrons or protons. Similarly, in cosmology, galaxies are something like the atoms of what we are studying, and its substructure, planets, stars, star clusters, etc., are not relevant for our study. So the third interesting feature about our universe is what we will be focusing on today, which is that we, as I said, we are immersed in an isotropic background radiation. And the characteristic of this radiation, it is thermal, which means its spectrum is a black body spectrum. And in fact, it was first detected by Penzias and Wilson. And this is a separate story in the history of science and history of cosmology. So having said this, let me now go over to the general plan of the talk. Okay, so first I will look at the broad framework to study the background universe. And then I will discuss what we call the ionization history. And from these two will emerge the topic of origin of cosmic microwave background radiation. It is isotropic, but only almost. It is unpolarized, almost. It has a black body spectrum, almost. Now, the reason why I have highlighted this is the following. You see, suppose you are looking at a building through thick fog on a winter morning. Now, the fact that there is fog, there is kind of almost a, I mean, to the first approximation, you do not see anything through the fog. And the fog is uniform. So this tells you something about the atmosphere. But still, through this uniform, there are slight deviations because of the background light coming. By studying these deviations, you can understand small features on this fog. So the overall isotropy has information about the background cosmology, and these small deviations from this isotropy or unpolarized nature or black body nature, slight deviations, give their own input about further details of the constituents of the universe. The constituent, the micro background also gives you information about things like cosmic magnetic field, gravitational waves, etc. But we won't have time to go through all those things. Okay. And okay. So now let us now go to the next one, which is let us set the stage for studying the cosmology, which is that we will discuss the expansion of the universe. Anil, you have not done Robertson-Walker metric and all, no?
No, Shesh. Just GTR part of it.
Okay, so okay. Now, of course, in order to study cosmology, one needs to do GTR, general relativity. However, it turns out that there is a simple hand-waving way in which you can get the equations governing the universe purely from Newtonian physics. Now, I won't go into the details of it, but there are some difficult. The reason why it is not usually done is that because it is not rigorously correct, but because of some strange coincidence, it gives the right answer and gives you some insight to the field. So I will follow that procedure. Okay. And so you'll call it expansion of the universe, Newtonian I'll call it pseudo derivation, because this derivation is not rigorously correct. Okay. So let us now look at this. Now I say that the universe is homogeneous and isotropic. That is, when I go from one point to another, when I say one point to another, I mean our cosmological distance scale like 100 megaparsecs, not to your neighboring house. So the universe, when I go from one point to other or cosmic scales, the universe looks identical, which is homogeneous. And when I look around from any point, the universe looks same in all directions. So it is isotropic. Now, a homogeneous universe is also spherically symmetric. See, a spherically symmetric object need not be homogeneous. That is, if I am sitting at the center of a spherically symmetric distribution, I move some distance, I am no more at the center. So it is not homogeneous. However, when it is homogeneous, it is still spherically symmetric. Okay? By spherical symmetry, I mean when I look around in all directions, it should be same. It is isotropic from a point. But the universe requires not only isotropy from a single point, but isotropy from all points, and hence it is homogeneous. Now I will use the fact that this homogeneous universe is, by corollary, also spherically symmetric. So now what I do is, I consider a point O, and I consider a test particle P, and draw a sphere okay. Yeah. And draw a sphere, the test particle, of radius r. Okay. Now let us denote by m mass contained in this sphere. Okay. And so I know from Newtonian mechanics, Newtonian gravity, that the dynamics of this particle depends only on the mass which is contained. Just a minute. Oh, recording. Anil?
Yeah, Shesh.
You are trying to record it, right? So it said recording failed. So I think it's okay now. Fine. Okay.
Okay.
Okay. So now, I don't know why something is not working. Just a minute. Okay. Okay. So, yeah, okay. There's something I was using a pointer which is not working. Okay. So now, the dynamics of this point is given only by the force because of the matter within within this sphere. So now, what is the potential energy per unit mass within this sphere? It is half, no, it is minus G by R into M, where M is the total mass in the sphere. Okay, so this is the potential energy, which is equal to G 4 pi rho R cube by 3 R. This is the potential energy with a minus sign. And this is because I have said that the universe is homogeneous, so the density is uniform everywhere, and that is why I can write this way. And the kinetic energy is half, since R is the distance between O and P, R dot is the velocity of P with respect to O. So the kinetic energy per unit mass is half into dr by dt whole square. And so half dr by dt whole square plus the potential energy, and the potential energy itself is negative. So I have G by R 4 upon 4 pi by 3 rho R cube. And this total is the energy in per unit mass in this sphere. Is this clear? Are people with me? Ayush Pandey, I was just randomly telling some names. Sanjay.
Students, if you are not able to understand, you can ask him, okay? Someone is giving thumbs up.
There is one, acha, oh, thumbs up, I see.
Yeah.
I was wondering what is the question. Okay. Okay. Fine. So now, so this is the thing. And remember that this is all per unit mass. Kinetic energy per unit mass, potential energy per unit mass, total energy per unit mass. So this is, and now what I can do is, I denote by R dot dr by dt. And so I can write this as half R dot square. This R and this R cube will make R square, and I'll bring it to the other side, minus G 4 pi by 3 rho is equal to E by R square. Okay. Right. Now, so look at the structure of this one. You see, when you do Newtonian mechanics, you have this concept of escape velocity. If the kinetic energy minus potentially, if the total energy is negative, it means that the kinetic plus potential energy is negative, and hence it will go to some height and then turn back. If this is positive, it will keep on going up, and at infinite distance, even when the potential energy goes to zero, there is a residual kinetic energy. However, if the potential energy plus kinetic energy is exactly equal to zero, the particle will still keep going up, but asymptotically, the particle will go to zero velocity. So when E is zero, it is something like R dot equal to escape velocity. It turns out that there is overwhelming evidence observationally, sorry, that E is equal to zero. Now, when you actually go into hardcore cosmology, this is what is called a flat universe. There are other reasons why you call it flat. Let me not go into that. Right now, we will just say that it is something like the by Hubble's law, where things are going away from each other, that velocity of recession is like equal to escape velocity for this universe. So this is one equation which we have. Okay. Now, but let me just put this equation in a slightly different form, which turns out to be more useful. Now, this quantity E equal to zero, which means that R dot square by R square is equal to 8 pi G by 3 times rho. Now, you can actually ask what happens to E equal to positive, negative. Then they give rise to something called a closed universe and an open universe, but I will not go for that because that will just complicate the issue. Now, this is basically to do with energy conservation. That is, total energy is E. But there is actually the other one, which is the equation of motion. And I will let us just look at that now. Okay, so again, this was the same thing, that you have a test particle and there's a point O and have drawn a sphere. Now, what is the acceleration for P? It is d2r by dt square, that is the second derivative of the radial distance, is equal to the gravitational force, which is minus gm, where m is the mass within the sphere, divided by r square. And this is minus g by r square, and as before, 4 pi r cube by 3 into rho, which is the mass. And if I simplify this, I will get, and I call this as r double dot. So I will have r double dot by r is equal to minus 4 pi r double dot by r is equal to 4 4 pi g rho by 3. Okay. So this is the other equation. So we have two equations. One is r dot square by r square is equal to minus 8 pi g by 3 times rho. And then I have r double dot by r is equal to minus 4 pi g by 3 times rho. Now, here, one needs to note something very interesting. You see, I started with a test particle and a point O. Now you can ask, what is so special about point O? What is so special about this test particle at a point P? And that is what I will address it now. Now, if you look at these equations, what comes is R dot by R and R double dot by R, which means if I multiply R by a constant alpha times R, the equations remain same. So it means, and so these equations cannot tell you about the value of R, which is what it should be. Because if we were to talk about a specific value of R, these equations do not have a universal validity over the entire cosmology. Since this R can be multiplied by any constant, these equations are true for any O and any P and any distance between them. So they have a universal validity. And because of this, conventionally, it is denoted by a quantity A, and the equations are A dot square by A square is equal to minus 8 by G by 3 times rho. A double dot by A is equal to minus 3 rho. Now, what is A? Now, A is called the scale factor, and I will just elaborate on it. Now, this scale factor is something like, it is only a measure of the size of the universe. It is not equal to the size of the universe, because size of the universe does not make any sense. What it says is, if A at T2 is equal to alpha times A at T1, any length scale, cosmological length scale L2 is equal to alpha times the cosmological length scale of L1. So A only gives you the ratio by which the universe has expanded when comparing at two different times, and not some physically measurable thing. Very roughly, it is something like the gauge freedom. If suppose you have, say, a potential. Now, absolute value of potential neither makes sense nor can be measured. What can be measured is the difference between potential at 2 points, and that is what leads to physical effect. Similarly, the value of A does not mean anything and cannot be measured. What is measurable is the ratio of A at two different times. So if you say that at T1 and at T2, the scale factors are AT1 and AT2, it means every length scale from T1 to T2 has expanded by a factor AT2 by AT1. So clearly I can multiply A by any constant, it will still be a scale factor. Is this clear? I mean, Anil, since you know them better. Anil?
Yeah, Shesh.
Is this okay? I mean, since you know them better, do you think I need any more explanation for this?
Ayush, it's fine.
Okay. Ayush?
Yeah,
Yes, sir,
I'm
it's
asking
fine.
this.
Okay.
Okay, I think they are
Okay.
able to understand.
Okay. So now this scale factor is a very central object when we are studying cosmology. So these equations are called the Friedmann, I mean, actually many people have contributed. So people say it is LFRW, Lemaitre, Friedmann, Robertson, Walker equations. Fine. Now, there is just one thing which I would like to mention. You see, when I did this entire derivation or pseudo derivation, I considered the mass as rho into a cube. What happens is, this is true only for the non-relativistic case. What in the case of relativistic case, we know that even the energy is some kind of a source like mass, E equal to mc square, very loosely speaking. And where does energy come from? The random energy comes from the pressure of the constituents, because the pressure has to do with the random kinetic energy density. It means that when the pressure is very high, the pressure itself has a gravitation component, because pressure is like energy density is like mass density, so that will also contribute. Now, pressure also has another role, which is to expand. So pressure is a kind of a double-edged sword. It tries to expand, but at the same time, when its value is very high, then the energy density tries to gravitate. And if you actually incorporate that, when you're doing general relativity, it comes as a natural consequence. But since we are doing a kind of a, as here we'll call a Jugad solution, this will get modified to a double dot by a equal to minus 4 pi r cube by 3. Sorry, 4 pi g by 3 into rho. But just like density, 3 times pressure will also lead to gravity. Actually, it will come as 3p by c square. Now, since c square is the large velocity, in non-relativistic case, this will not contribute and we will get this result which we wrote. However, in a relativistic case, if the pressure is very high, this will also contribute, and this is the complete equation for cosmology. Okay. Now, okay, Anil, what I will do is the following. I will talk about the radiation, matter, and the time temperature relationship, and the ionization history I will start tomorrow. Is that okay?
Okay, Shesh. Okay.
Yeah, because it's an overdose right now.
Yeah. Okay, Shesh.
Fine. So now, what are the consequences of this? Okay. Now, so I will say, so these are also called, I mean, Einstein's equation for cosmology. Okay, so I will, let me just say LFRW equations and their consequence. Okay. Now we have a dot square by a square is equal to 8 pi g by 3 times rho. And I have a double dot by a is equal to minus 4 by 4 pi g by 3 times rho plus 3p. Now I have taken c equal to 1. Anil, are they familiar with this thing?
Yeah, Shesh. Yeah.
Okay. So I will take c equal to 1. So all velocities I will measure in units of c. Okay. And so I can get rid of the c. It's easy for calculation. Now, there is another equation which is required, because here I have a pressure and a density and there is no relationship I know between them. Now, for this, what you do is, let me again, there is a rigorous way to do it, but let me just do it a hand waving classical way to explain to you. Rho is the energy density per unit volume. Say mass per unit volume, so it's equal to energy per unit volume. Energy per unit volume, not energy density, but energy density. And A is a typical length scale. Okay? So A of t tells you how the universe expands or contracts. And hence, A cube is a volume scale. So I can say that rho into A cube is something like energy in a certain volume, the volume given by A cube. Okay. Now, P is the pressure and P dV is the work done. And so this is P d of A cube because A cube is the volume. Now, change of energy plus work done should be 0, which is what is energy conservation. And so I have d rho A cube plus P d A cube is equal to 0. And this is basically the various, you can call it the first law of thermodynamics, or I can call it energy conservation. Okay?
It's basically dW plus PdV, isn't it, sir?
Yes, this is basically dE plus PdV equal to 0. Okay, now I should mention one important thing. See, actually dE plus PdV is TdS, temperature into change in entropy. But here we are assuming a completely an adiabatic process. You know, there are certain situations in cosmology where this is violated, but I will not be considering those intricacies right now. For most of the history of the universe expands as an adiabatic system, and so ds is 0, and so dE plus P dV is 0. That is, the change in energy is purely because of the work done. Is it okay, Anil?
Yeah, Sheshadri.
Yeah. Okay. Fine. But now, in order to solve this, I need a relationship of pressure as a function of density. And this is called the equation of state. And so what I do is, okay, so now let us consider a case of radiation. In the case of radiation, we know that P is equal to 1 by 3 rho by c square, which in my units of c equal to 1, I have put it as 1/3 rho. Now, if I have pure matter, I have pressure equal to 0, because if suppose I have a dust, then there is no random kinetic energy, so pressure is 0. Let us now see how this plays out. Now, let us consider radiation with this equation. So I have d rho A cube plus P d A cube is equal to 0 implies P rho A cube plus 1/3 rho d A cube equal to 0, and you can solve this and you will get rho proportional to 1 by A4. It means as the universe expands, the density of radiation goes down as 1 by A power 4. This is a very important information hidden in this, which I will just come to. But first, let me now consider the case of pure matter together with this equation. So I have d rho a cube plus p dA cube equal to 0, and P equal to 0 for matter implies rho proportional to 1 by A cube, which is more familiar. It says that if the universe expands, the linear scale expands as A, volume expands as 1 by A, and the density decreases as 1 by volume, which is, sorry, volume expands as 1 by A cube, and the density decreases as 1 by volume, which is 1 by A cube, which is fine. But then why is it different from these two? Why rho radiation goes as 1 by A4 and rho matter goes as 1 by A cube. And there's a very interesting thing here. Let us now look at, instead of density, let me look at the number density of particles. Now, number density of particles will always go as 1 by A cube, whatever be the system. If the number of particles per unit volume, if it becomes bigger, the number of particles, total number of particles remain conserved. So this happens. It means, now, so suppose in rho radiation, suppose I consider, for example, radiation with of frequency nu. It means that if n gamma is the number density of photons and nu is the frequency, then the density of the photons will be equal to number density of photons and the energy of each photon, which is h into nu. Now, I already saw that this goes as 1 by A4. I already saw that this goes as 1 by A cube, which says something very interesting. It means the frequency of individual photon should decrease as 1 by A, which means as the photon propagates, its frequency is decreasing and its wavelength is increasing. And this is what we all know as cosmological redshift. When we see what Doppler thought was, what Hubble thought was a Doppler redshift is incorrect. Because Hubble did it in a, he considered a flat universe which was expanding. According by Einstein's theory, it is not the case. In Einstein's theory, the redshift is there, but the origin is not Doppler, but the origin is cosmological. Now, for the nearby universe, the Hubble interpretation is same as what Einstein's interpretation to a good approximation. And that is why Hubble thought it was Doppler. But in reality, this is not Doppler. It is actually cosmological, and this gives you a reason why the frequency of radiation goes as 1 by A as universe expands. On the contrary, the rho of matter is equal to number density of matter particles times mass of every particle. Now, mass of every particle remains conserved as the universe expands. So, and since this goes as 1 by A cube, this also goes as 1 by A cube. This is the reason why radiation goes as 1 by A4 and matter goes 1 by A cube. And that is, it is because every particle of radiation, which is a photon, individually its energy is decreasing as 1 by A, whereas the individual energy of a matter particle remains constant. And that is why this difference is there. Okay. Okay. So let me just go over to uh, how the expansion takes place, then I will stop. So I will call it from equation of state to cosmic expansion rate. So now suppose I take the case of matter, and if I write P is equal to W times rho, then for matter, I saw that W equal to 0. And the conservation of energy, d rho A cube plus P dA cube equal to 0. When I put it here, I will get rho proportional to A to the power minus 3, which we just saw. And now I already saw the Friedmann equation as A dot square by A square is equal to 8 pi g by 3 times rho. And now if I put for rho as 8 pi g by 3 times some constant by A cube, which is this one. And then I can solve this equation for A as a function of t, and I get A proportional to t to the power 2 by 3. So this simple argument tells me that first of all, with time, A is increasing, which means that the universe is expanding. And it tells you how, at what rate the universe is expanding. But now, let me consider radiation. I have got, for radiation, I have W equal to 1 by 3. If I now put this equation here, as I saw, I get rho proportional A power minus 4. And if I substitute this A power minus 4 here, I will get A is proportional to T to the power half. It means that depending on what kind of material, what kind of constituent dominates the universe, the expansion of the universe is accordingly different. If we have a universe full of radiation, it will go as A proportional T power half. It is pressureless matter. It will go as T to the power 2 by 3. In general, we have A proportional to T to the power n is less than 1. Now, n less than 1, what does this imply? If n is less than 1, it means A dot by A is equal to proportional to n by T. Okay. And, what am I talking? Sorry. Is proportional to n T power. No, that is correct. Yeah. I mean, the statement should be different. I mean, A dot is proportional to n T power n minus 1. A double dot is proportional to n into n minus 1 T to power n minus 2. If n is less than 1, and from here we have A double dot less than 0. It means that for all kind of normal matter in the universe, since n is less than 1, we have an expanding universe but a decelerating universe. A double dot less than 0. Now, you people must have heard of accelerated expansion, dark energy, and so on. That is a proposition where you introduce a matter with n greater than 1, which makes A double dot greater than 0 and hence an accelerated universe. But we will not go into that right now. That's a very speculative. So I think I will end my talk today, and tomorrow I will start talking about the time temperature relationship and hence what happens to the ionization history of the universe and what are its consequences. Yeah. Any questions?
Okay, if you guys have any questions, you can ask. Please don't hesitate, okay?
Yeah, just ask. Yeah.
No, just ask. No problem.
You see, I will tell you one thing. You people are in an age where if you nobody will tell you that's a stupid question because you're starters. When you become an old man like me, then you can hesitate because people say, "Abhi tak kya sikha hai?" So that is the advantage of being young. You can just ask whatever question you want. Okay, so let me.
You can unmute yourself and then ask. No problem.
Yeah. Ayush, Anuj. What is it? Cos? Oh, yeah.
It's not real name, Sesh.
I know it is. Maybe Subhash. So it is Subhash inside Cosmos, maybe.
Might be.
Okay.
Subhas is in Cosmos. Okay.
Hey, Subhash, is that true? What I'm saying?
Please don't hesitate. It's your opportunity, okay? You guys can ask any questions.
Then there's a guy called Lenovo, which is the person's laptop. Nishchal, Shrestha, Pratik.
Yeah, someone is asking. Okay.
Yes.
So you said that the derivation using the Newtonian method, this is not like as rigorous. So are there like any faults you could like point to in this derivation?
Yeah. I mean, the reason is the following. You know,
truly
when
correct
you
and stuff.
say that only, is in Newtonian thing, when you say that only that portion of the thing which is within the sphere is gravitating, you know, in the case of Newtonian thing, you are making an assumption that at infinity the potential vanishes.
Yeah.
It is true only if you have a localized matter. But in cosmology, you have an infinite distribution of matter. So there are a bit of problems there. Okay, that is the catch.
So cell theorem is not truly valid in cosmology.
Which one?
Cell theorem.
He's still talking about that Newton's shell theorem, like point mass can be that spherical distribution can be.
Acha. I mean, because the point is Newton's thing is valid only for a finite distribution of matter, not an infinite distribution of matter.
Yeah, so matter itself extends to infinity, so you
Yes,
can't say
that's the problem.
zero. Yeah. Okay.
In Newtonian theory, there is not exact answers, I think. But if you have a uniform density in the universe, then the universe will self-expand, isn't it, Says?
I mean, it will. No, because it's an initial kick which has been given in Big Bang, because of which it is expanding. Yeah.